Hi, and welcome to the presentation on plotting positions for systematic data. My name is David Margot, and I'm a lead civil engineer with the Risk Management Center. In this presentation, we're going to take a bit of a deeper dive into various plotting position formulas and their underlying meaning and interpretation. I have three primary goals for this presentation. The first is that you will be able to summarize the interpretations behind the various plotting position options for systematic data. Second is I would like you to understand how you can explore and verify the various plotting position formulas using a Monte Carlo analysis. And lastly, I want you to be aware of plotting position uncertainty and how it might affect your interpretation of a frequency analysis. During the presentation, we'll cover 5 of the commonly used plotting position formulas for systematic data in hydrology. For some of these plotting position formulas, we'll explore them further with a Monte Carlo analysis. And then we'll wrap up the presentation with a discussion of plotting position uncertainty. Let's start with a quick refresher on plotting positions. Plotting positions provide us with an estimate of the exceedance probability or the annual exceedance probability for observed events. We can use them to develop an empirical frequency curve, or we can use them to provide a visual comparison with a computed analytical frequency curve, such as a flow frequency curve computed using the methods in Bulletin 17C. Here is the general plotting position formula that can be used for systematic data. The F term on the left-hand side of the equation is the plotting position, which is also the exceedance probability or the annual exceedance probability. The I term is our ranking of the data from the largest observed event to the smallest observed event. N is the total number of data or the total number of observed events. And A is a parameter that we use to define the type of plotting position we would like to calculate. The first plotting position formula we'll take a look at is the WEIBULL formula, which has an A parameter equal to 0. The WEIBULL plotting position answers the following general question. What is the expected value of the smallest annual exceedance probability drawn from a sample of n observed events? Of course, we're interested in the plotting position for all the observed events, so we'll also look at the second smallest, the third smallest, etc. Now keep in mind that the smallest AEP value corresponds to the largest observed event. So the largest observed flood event will have the smallest AEP value, or the smallest plotting position. We can take a closer look at the WEIBULL plotting position formula using a Monte Carlo analysis. In this analysis, we start by generating n random samples of annual exceedance probability from a uniform distribution between 0 and 1. From those n samples, we then calculate the smallest annual exceedance probability value. We repeat that process for 1,000 realizations, recording the smallest AEP value for each realization. We can then calculate the average of these smallest AEP values over all of the realizations. And again, remember that the average of these smallest AEP values correspond to the largest flood event. So the value we calculate should be equal to the WEIBULL plotting position for the largest data value, or the largest observed event, which has a ranking of 1. Here's a look at the results of a Monte Carlo analysis for a sample size of 30. So in this analysis, we generate 30 random samples of AEP, and we record the smallest AEP value. That's the result for one realization. We then repeat this process for 1,000 realizations, recording the smallest AEP from each realization. We can then calculate the average of these smallest AEP values over all of the realizations and report that number. We can also compare the result to the result we get from the WEIBULL plotting position formula with n equals 30, a rank of I equals 1, and the A parameter equal to 0. And you can see in this example that the two results are essentially the same. The small difference is due to sampling error based on the number of realizations. If we wanted a more accurate comparison, we would simply have to do more realizations. The median plotting position formula has an A parameter equal to 0.3, and it answers a question similar to the WEIBULL plotting position formula, except in this case we are now asking what is the median value of the smallest annual exceedance probability drawn from a sample of n observed events. And again, remember that the smallest AEP value will correspond to the largest observed event. We can look at the median plotting position formula with a Monte Carlo analysis. And since this analysis is similar to the analysis we would do for a WEIBULL plotting position formula, we can simply use the results we generated previously for the WEIBULL plotting position example. The only minor difference in this example is that in the figure on the right, instead of calculating the expected value or average over all of the realizations, we now calculate the median value of the smallest AEP values. Again, we can compare this result to the result we get using the median plotting position formula for the largest flood event, which would have a ranking of I equals 1, a total number of data equal to 0, and an A parameter equal to 0.3. When we do this comparison, we can see in this case that the two results are the same. For the BLOM plotting position formula, we have an A parameter equal to 0.375. This formula answers the following general question. What is the annual exceedance probability of the expected value of the largest observed data value given a sample size of n events drawn from a normal population? So for this type of plotting position, it is dependent on the assumed parent population, which in this case is a normal distribution. So again, we can use a Monte Carlo analysis to further explore the BLOM plotting position formula. We start by generating n samples of annual exceedance probability from a uniform distribution. We then have to calculate n corresponding values of x, our variable of interest, assuming that we have a normal population with a given mean and a given value for standard deviation. From those n samples of x, we can then calculate the largest x value. We repeat that process for 1,000 realizations, recording the largest x value for each realization. After that, we can calculate the average of all the largest x values over all of the realizations. We then calculate the annual exceedance probability of this average x value, again assuming that we have a normal distribution with a given mean and a given standard deviation. This AEP value will equal our plotting position value. Here's a look at the results from the Monte Carlo analysis. So in the figure on the left, we start again with a sample size of 30 by generating 30 random samples of AEP. Then in the figure on the right, we calculate corresponding values of x, assuming that we have a normal distribution with a mean of 0 and a standard deviation of 1. From those values of x, we identify the largest x value that corresponds to the smallest AEP value and record it as the result for that realization. The process is repeated for 1,000 realizations, and we then calculate the average of the largest x values over all of the realizations. We then plug that largest x value into our normal distribution with a mean of 0 and a standard deviation of 1 to get an estimate of the annual exceedance probability. So in this example, the average of the x values is equal to 2, and given that we have assumed a normal distribution with a mean of 0 and a standard deviation of 1, the AEP of our average x value is equal to 0.02, which compares well with the result we get using the BLOM plotting position formula with a ranking of 1 for the largest event, a sample size of 30, and a value of 0.375 for the A parameter. The next plotting position formula is the GRINGORTEN formula, which has an A parameter equal to 0.44. This one is similar to the BLOM formula, except that it is specific to either a Gumbel distribution, which is an extreme value type 1 distribution, or an exponential distribution. The last plotting position formula we're going to take a look at today is the Cunnane formula, which has an A parameter equal to 0.4. This is proposed as a reasonable compromise for the distributions that are commonly used in flood hydrology. So what makes this a reasonable compromise? Well, as we saw with the BLOM formula, for normal and log normal distributions, the A value should be 0.3. We also saw with the GRINGORTEN formula that for Gumbel distributions and exponential distributions, an appropriate value for A is 0.44. The log Pearson type 3 distribution should be somewhere between these two values, depending on the value of skew. When skew is equal to 0, the log Pearson type 3 defaults to a log normal, and the A parameter should be closer to 0.3. When the skew value gets relatively large, either a large positive value or a large negative value, the log Pearson type 3 distribution behaves more like an exponential distribution, which would have an A value of 0.44. So the proposed value of A of 0.4 lies somewhere in the middle of 0.3 and 0.44, which is the rationale for it being a reasonable compromise. So given all these choices among the various plotting position options, which one is the best? Well, in this presentation, we're not going to make any specific recommendations on which plotting position you should use. I will say that in many cases, the differences aren't all that significant, and it usually doesn't make that much of a difference in terms of your analysis, your interpretation of the results, or the decisions that you're making from that analysis. What is important, I think, is that you understand the underlying basis and motivation and interpretation for each of the plotting position options so that you can make an informed choice for your particular study. Now let's transition to look at plotting position uncertainty. We can use our WEIBULL Monte Carlo experiment to explore the uncertainty in the AEP value for the largest flood event. So the figure on the left is the same results from our WEIBULL Monte Carlo experiment where we had a sample size of 30. We extracted the smallest AEP value, which represents the largest flood event, over 1,000 realizations. We can take that data and plot it as a probability distribution, which is the figure shown on the right-hand side. From this distribution, we can look at the 90% confidence interval to get a sense for how much uncertainty there is in the AEP for the largest flood event out of 30. And in this example, you can see that the uncertainty spans nearly 2 orders of magnitude, which is a pretty significant amount of uncertainty in the estimate. Now that we know that our plotting position uncertainty can be quite large for the largest observed flood event, we can look at how this uncertainty changes as we move down through the ranking of the events. So the figure on the left is the same figure from the previous slide where the uncertainty in AEP spans nearly 2 orders of magnitude. When we move down to the 5th largest event, we can see that that uncertainty decreases quite a bit. So in the figure on the right, we see the uncertainty in AEP for the 5th largest event, over 1,000 realizations, where the 90% confidence interval spans about 1/2 order of magnitude. So keep in mind that the largest events will have the greatest uncertainty in plotting position, and that uncertainty will decrease as you move down through the ranking of the events. So here is a visual depiction of the plotting position uncertainty. So in the figure on the left, we can see the plotting position uncertainty depicted for the largest observed flood event, and we can see that it's quite large. In the figure on the right, we can see that uncertainty depicted for the top 3 flood events, showing that the uncertainty decreases as we move down through the ranking of events. These are 2 of the key takeaways when it comes to plotting position uncertainty. The first is that plotting position uncertainty is very large for the largest observed flood events. And second, this uncertainty decreases as we move down through the ranking of the events. This concludes the presentation on plotting position uncertainty. If you're interested in doing some additional reading, I would recommend that you start with the paper referenced here, Unbiased Plotting Positions, a Review. Thank you for your time and your attention.